Welcome back, tech enthusiasts, to another exciting episode of TechNation. Today, we're about to embark on an astronomical journey that's guaranteed to leave you burning with curiosity. Get ready to peel back the layers of celestial mystery as we decode the fiery enigma that is the scorching hot sun. We're delving into the heart of our solar system, armed with curiosity and a thirst for knowledge. So, grab your SPF-infused popcorn and settle in as we uncover the secrets behind the sun's sizzling temperatures. But fair warning, you might want to leave your marshmallows at home because this inferno is no ordinary campfire. The sun, that massive celestial ball of fire and light, has captivated human curiosity for millennia. One of the most intriguing aspects of this cosmic powerhouse is its intense heat. Just think about it. A single star, located millions of miles away from Earth, radiates such incredible temperatures that it can scorch anything in its path. But why is the sun so incredibly hot? The sun's heat is not just a matter of mere warmth or comfort. It is a force that shapes our entire existence. From providing the energy necessary for life on Earth to driving weather patterns and climate cycles, the sun's heat influences every aspect of our planet. Understanding the source and magnitude of this heat is crucial for comprehending the fundamental workings of our universe. To comprehend the sun's intense heat, we must first grasp its nature as a star. The sun is a gigantic fusion reactor, where mind-boggling nuclear reactions take place at its core. These reactions involve the fusion of hydrogen atoms, converting them into helium and releasing an immense amount of energy in the process. The mind-blowing temperatures generated within the sun's core, reaching millions of degrees Celsius, are a result of this ongoing fusion process. The sun, our nearest star, is a magnificent celestial object that holds a crucial role in our solar system. To understand its intense heat, we must first grasp the nature of the sun as a star and its significance in the cosmic ballet that governs our existence. At its core, the sun is a massive ball of glowing gas, primarily composed of hydrogen and helium. It belongs to the class of stars known as G-type main sequence stars, or more commonly referred to as yellow dwarfs. While it may appear as a mere bright disk in the sky, the sun is an astronomical powerhouse, emitting an astounding amount of energy. The sun's main role in our solar system is to provide light and heat, which sustains life on Earth. Its rays travel through the vast expanse of space, bathing our planet in sunlight. This energy is vital for photosynthesis, the process by which plants convert sunlight into the chemical energy necessary for growth and sustenance. It also plays a significant role in weather patterns, climate systems, and the water cycle. To understand why the sun is so incredibly hot, we need to explore the concept of nuclear fusion, the primary source of the sun's heat. Nuclear fusion is a process in which atoms combine to form heavier elements, releasing a tremendous amount of energy in the process. In the case of the sun, hydrogen atoms fuse together to form helium, liberating an enormous amount of energy. Deep within the sun's core, temperatures reach mind-boggling levels, exceeding millions of degrees Celsius. Under these extreme conditions, hydrogen atoms collide with such force that they overcome the electrostatic repulsion between their positively charged nuclei. As a result, the atomic nuclei fuse, forming helium atoms. This intricate process of nuclear fusion relies on the sun's immense gravitational pull. Gravity compresses the sun's core, increasing its density and temperature. The immense pressure at the core causes hydrogen atoms to move at high speeds, leading to frequent collisions and fusion reactions. This continuous fusion process releases a tremendous amount of energy in the form of light and heat. The temperatures generated by these fusion reactions within the sun's core are truly staggering. They reach levels that are difficult for our human minds to comprehend. For comparison, the core of the sun is approximately 15 million degrees Celsius, which is more than 27 million degrees Fahrenheit. These mind-boggling temperatures are the result of the colossal energy released during the fusion of hydrogen atoms into helium. These extraordinary temperatures and the energy they produce are what give the sun its intense heat. It's the driving force behind the sun's ability to sustain life on Earth, influence climate systems, and power the processes that shape our planet. To truly understand the sun's intense heat, we must take a deep dive into its core, where a complex interplay of structure, composition, and forces shape its remarkable characteristics. The sun's core, located at its very center, is a region of extreme density and temperature. It comprises about 25% of the sun's total radius but holds an astounding 99% of its mass. Within this compact core, gravitational forces play a pivotal role in creating tremendous pressure. Gravity, the force of attraction between objects with mass, is responsible for pulling matter inward toward the core of the sun. As mass accumulates and is compressed by gravity, the pressure within the core becomes immense. The combined weight of the sun's outer layers exerts a tremendous force, compressing the core and increasing its density. At the core center, hydrogen atoms are subjected to these intense pressures and temperatures. Hydrogen, the most abundant element in the sun, serves as the primary fuel for the sun's nuclear fusion reactions. Fusion is a process where atoms combine to form heavier elements, releasing energy in the process. Within the core's extreme conditions, hydrogen atoms collide with each other at high velocities due to the thermal energy present. These collisions overcome the electrostatic repulsion between the positively charged atomic nuclei, allowing them to get close enough for the strong nuclear force to bind them together. This fusion process results in the formation of helium atoms. The conversion of hydrogen into helium through fusion is the key source of the sun's energy. During fusion, a small fraction of the hydrogen's mass is transformed into energy according to Einstein's famous equation, E = mc squared. This equation states that mass and energy are interchangeable, and even a small amount of mass can release a tremendous amount of energy. The released energy in the form of photons, light particles, is what gives the sun its intense heat. These photons travel outward from the core through a process known as radiative transfer, eventually reaching the sun's surface and escaping into space as sunlight. The energy released during fusion provides the sun with a constant supply of energy, which fuels its luminosity and sustains its temperature. It takes millions of years for this energy, generated at the sun's core, to reach its surface due to the slow diffusion of photons through the dense layers of the sun's interior. The sun's equilibrium is a delicate balance between the inward gravitational forces and the outward energy released by fusion reactions. Understanding this balance is crucial for comprehending how the sun maintains its stable state, preventing it from collapsing or expanding uncontrollably. Gravity, a fundamental force in the universe, is responsible for the formation and structure of celestial bodies. In the case of the sun, gravity is continually pulling matter inward toward its core. The immense mass of the sun exerts an enormous gravitational force, compressing the core and increasing its density. At the same time, the sun's core is a hotbed of nuclear fusion reactions, primarily involving the conversion of hydrogen into helium. Fusion releases an enormous amount of energy in the form of light and heat. This energy pushes outward, counteracting the force of gravity. The equilibrium between gravity and fusion reactions within the sun's core is crucial for maintaining its stable state. If the force of gravity were to overpower the energy released by fusion, the sun would collapse under its own weight. Conversely, if the energy from fusion were to surpass gravity, the sun would expand uncontrollably. The sun's equilibrium is achieved through a fine-tuning of its internal conditions. The core's temperature and density play crucial roles in this delicate balance. The temperature determines the rate at which fusion reactions occur, while the density affects the efficiency of energy transfer. If the sun were to collapse, the core would become denser and hotter, increasing the rate of fusion reactions. This accelerated fusion process would release more energy, creating an outward pressure that counteracts the inward pull of gravity. As a result, the sun would expand, which in turn would cool and decrease the rate of fusion. Conversely, if the sun were to expand, its outer layers would become less dense. This would reduce the rate of fusion reactions, leading to a decrease in energy production. With less energy to counteract gravity, the sun would start to contract, increasing its density and temperature. This contraction would raise the rate of fusion reactions, thereby releasing more energy to push against gravity and restore equilibrium. The delicate balance between gravity and fusion reactions allows the Sun to remain stable over long periods. While there are minor fluctuations in its size and luminosity, the overall equilibrium is maintained, providing a relatively constant energy output. This equilibrium is crucial for the Sun's role in our solar system. It ensures a stable source of heat and light, allowing for the existence of life on Earth. The Sun's equilibrium also impacts the stability of orbits for planets and other celestial bodies within the solar system. Additional factors play a role in determining the Sun's heat, including its size, mass, and age. Furthermore, there exists a correlation between a star's temperature and its luminosity. Higher temperatures result in increased luminosity, meaning that hotter stars emit more light and energy. This relationship between temperature and luminosity holds true for the Sun as well. The Sun's temperature has a significant impact on Earth, particularly regarding climate and weather patterns. The Sun's energy drives the global climate system, influencing temperature variations, wind patterns, and the water cycle. Understanding the Sun's heat is crucial for predicting and interpreting weather phenomena, such as hurricanes, tornadoes, and atmospheric circulations. The Sun's heat also influences biological processes, including growth, development, and reproduction. Solar energy has immense importance for various technological applications as well. Solar power, harnessed through photovoltaic cells or solar thermal systems, provides a renewable and clean source of electricity. Understanding the Sun's heat and its variations is crucial for optimizing solar energy technologies and improving their efficiency. And there you have it, folks. We've journeyed through the intriguing world of the Sun's intense heat, unraveling its secrets one witty explanation at a time. From its core to its impact on Earth, we've explored the cosmic dance between gravity, fusion, and temperature. So the next time you bask in the warmth of the Sun or marvel at a breathtaking sunset, remember the delicate balance that keeps our star shining bright. Now, armed with a deeper understanding of the Sun's fiery enigma, you can impress your friends with your solar knowledge. Just make sure not to blind them with science, unless you're equipped with a pair of solar-powered sunglasses. As we conclude this cosmic adventure, let's appreciate the Sun's role as our celestial companion, heating our planet, powering our lives, and even inspiring some questionable sunburns during those beach vacations. Soak up the sunshine, but always remember to protect your delicate human skin with some SPF-infused wisdom. Stay curious, stay witty, and keep exploring the wonders of our universe. Until next time, fellow astrophiles, may your days be sunny and your minds enlightened. Shine on!